Hello, good morning, everybody. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE. Today, I am going to discuss on the question bank of Unit 1, that is diode applications. So, the first question is compute the value of DC resistance and AC resistance of a germanium diode at 25 degrees centigrade with a reverse saturation current I0 equal to 25 microamperes at an applied voltage of 0.2 volts across the diode. Now I'll give you the solution for this. So in this problem, I0, which is the reverse saturation current, that is given as 25 microamperes, and the temperature is given as 25 degrees centigrade, and it is a germanium diode, and the applied voltage is 0.2 volts. This is the applied voltage. Now with these conditions, let us find out the DC resistance and AC resistance. Resistance is nothing but voltage by current. Voltage is already given as 0.2 volts. Now let us find out the current. So what is the equation for current? I0 equal to, which is the reverse saturation current. So I is equal to I0 into e power v by eta Vt minus 1. So this is the equation, and from this equation let us find out the diode current. First, let us find out what is the value of Vt. See, Vt is equal to T by 11,600. What is T? T is the temperature in degrees Kelvin. So, 273 we have to add to 25 to get temperature in Kelvin divided by 11,600. So, this works out to be 0.02568 volts. So this is approximately 26 millivolts. So I will use this value in the diode equation, which says I0 into e power v by eta Vt minus 1. So that is equal to I. So I is equal to I0 into e power v by eta Vt minus 1, and I0 is a 25 microamperes, so 25 into 10 power minus 6, and e power v is 0.2 volts, and eta is 1 for germanium, so 1 into 26 millivolts minus 1. So this is equal to 54.79 milliamperes. So this is the current at the bias of 0.2 volts. Now let us find out what is the DC resistance. So RDC, which is the static resistance, is nothing but V by I, and V is given as 0.2 volts. So divided by 54.79 milliamperes. So this is equal to 0.2 by 54.79. So that works out to be 3.65 volts. So this is the static resistance. Now the dynamic resistance is given by this formula. RAC is equal to eta Vt by I, and eta is equal to 1 for germanium, and it is 2 for silicon. So eta Vt 1 into 26 millivolts And I already we have calculated as 54.79 milliamperes. So if you calculate this, you will get 0.47 ohms. So this is the DC resistance and this is the AC resistance. AC resistance is also called as the dynamic resistance. Now let us move on to the second problem. The second problem is the reverse saturation current of a silicon PN junction diode at an operating temperature of 27 degrees centigrade is 50 nanoamperes. Compute the forward and reverse dynamic resistances of the diode for applied voltage of 0.8 volts and minus 0.4 volts. So here you have to find out the dynamic resistances, and for 0.8 volts we get the forward dynamic resistance, and for minus 0.4 volts we get the reverse dynamic resistance. The forward dynamic resistance, naturally it will be less compared to the reverse dynamic resistance. So here we have to calculate the value of Vt first. Vt is nothing but voltage equivalent of temperature, and that is given by T by 11,600. So first let us calculate Vt. T divided by 11,600. So T is 273 plus 27 divided by 11,600. So this is approximately 0.026 volts. So that is equal to 26 millivolts. So there is a voltage equivalent of temperature. Now I is equal to, which is the diode current, that is given by the diode equation, I naught into e power V by eta Vt minus 1. Now let us first calculate the diode current for 0.8 volts. Then we will calculate the diode current for minus 0.4 volts. So I at 0.8 volts is given by I naught, which is given as 50 nanoamperes, and e power V. V is 0.8 volts, and this is the silicon, so we have to take the value of eta as 2, and Vt is 26 millivolts minus 1. So this is equal to 239 nanoamperes. Now let us calculate the diode current for the reverse voltage of minus 0.4 volts. So I at minus 0.4 volts is given by I naught into e power V by eta Vt minus 1, and I naught is 50 nanoamperes, and e power V. V is how much? Minus 0.4 volts, and eta is 2, and Vt is 26 millivolts minus 1. So this we get approximately as 50 nanoamperes. This is approximately 50 nanoamperes. Now let us find out the forward and the reverse resistances. So RAC at 0.8 volts is equal to, this is a formula for the dynamic resistance, eta Vt by I. So this is equal to 2 into Vt we have already calculated, and that is equal to 26 millivolts. And current we have calculated, and the current has come 239 nanoamperes. So 239 nanoamperes. So this is equal to 0.217 ohms. So this is the value. Now similarly, let us calculate RAC at minus 0.4 volts. So this is equal to eta Vt by I. So eta is equal to 2 and 26 millivolts, and current is 15 nanoamperes. So 15 into 10 power minus 10. So this will come approximately 1.04 megawatts. So this is the solution for this problem. Next, let us go to the question number 3. That is, a full wave single phase rectifier makes use of two diodes. The internal forward resistance of each is considered to be constant and is equal to 30 ohms. The load resistance is 1 kilo ohm. The transformer secondary voltage is 200-0-200 volts. Solve for IDC, VDC and the ripple factor. So this is the problem. So here, okay, let us not take RMS value, let us take this the amplitude. Let us take this as amplitude. Okay. Now under this assumption, let us find out the solution, and let us also assume that the full wave rectifier is provided with a center tap transformer with transformer turns ratio 10:1. So assume the turns ratio is 10:1. So with these assumptions, let us calculate the parameters IDC, VDC and the ripple factor. What is the circuit diagram for the full wave rectifier? This is a circuit diagram for the full wave rectifier. It uses the center tap transformer and it has the two diodes, and the center of the transformer is grounded. This is another diode, and this is the load resistance RL, and this is the ground point, and the output is taken across the load resistor. And we have assumed that the transformer secondary voltage is 200-0-200 amplitude, and the turns ratio is 10:1. So first let us calculate the IM value. So IM is equal to VM divided by RF, that is the forward resistance of the diode, plus RS, there is a transformer coil resistance, plus RL. So we also assume that the secondary coil transformer resistance is negligible, so we replace it by 0. So this is equal to 200 divided by 10, because the transformer turns ratio is 10. So 200 by 10 divided by the forward resistance of the diode is 30 ohms plus The load resistance is 1 kilo ohm. So this is equal to 20 divided by this 30 ohms plus 1 kilo ohm. So we write it as 1.03. So that is equal to 19.41 milliamperes. So that is the peak value of current. So how do you calculate the DC value of the current? IDC is equal to 2Im by pi. So that is equal to 2 into Im, that is 19.41 milliamperes divided by pi. Pi is 22 by 7, which is nothing but 3.143. So this we get as 12.4 milliamperes. That is the DC value of current. Next, let us find out what is the average DC voltage. So average DC voltage is nothing but IDC multiplied by RL. So when you multiply IDC with RL, you get VDC. So VDC is equal to IDC multiplied by RL. So IDC is 12.4 milliamperes and RL is the load resistance, which is given as 1 kilo ohm in the problem. So here we get the DC voltage as 12.4 volts. That is the DC voltage. Next, we are supposed to calculate the ripple factor. So ripple factor we calculate in this way. Ripple factor is equal to IRMS divided by IDC whole square minus 1, and we take the square root of this. And what is IRMS? IRMS is equal to Im by root 2 for full wave rectifier. For half wave rectifier it is Im by 2. For full wave rectifier it is Im by root 2. So IRMS is equal to Im by root 2. Then IDC is equal to 2 Im by pi. We substitute same thing for IDC. Pi by 2 Im whole square minus 1. So this is equal to pi square by 8 minus 1. So the ripple factor we get as 0.48. Ideally the ripple factor should be 0, or it should be as small as possible, so that the DC output is constant and it is smooth. So here we have got the ripple factor as 0.48, so which is quite reasonable, and the output quality of the voltage is better. Now let us do this question number 4. It is a half-wave rectifier is used to supply 24 volts DC to a resistive load of 500 ohms, and the diode has a forward resistance of 50 ohms. Calculate the maximum value of AC voltage required at the input. It is a half-wave rectifier. What is the circuit for half-wave rectifier? This is a circuit for the half-wave rectifier. This is a load resistance RL and it has only one diode. So the average value of current IDC is equal to VDC by RL, and VDC is given as 24 volts in the problem and RL is 500 ohms. So IDC is equal to 48 milliamperes. So what is the maximum value of load current? Im is equal to pi into IDC. So pi into 48 milliamperes. So that is equal to 150.8 milliamperes. Because IDC is equal to Im by pi for half wave rectifier. So Im is equal to pi into IDC. So pi into 48 milliamperes. So that is equal to 150.8 milliamperes. So the maximum AC voltage required in the input is Vm is equal to Im into Rf plus RL, and Im we have already calculated, and that is nothing but 150.8 milliamperes. So into 550, so that voltage comes to 82.94 volts. Question number 5 is regarding the full wave rectifier. So a full wave rectifier has a center tap transformer with 100-0-100 volts. So we assume that 100 as amplitude, and each one of the diode is rated at Imax of 400 milliamperes. So neglecting the voltage drop across the diodes, solve the efficiency, DC output voltage and DC current and PAV of each diode. So let us solve this problem. So here at the maximum value of current, that which is 400 milliamperes, what should be the load resistance? Let us calculate. So RL is equal to 100 by Im. Im we take it as 400 milliamperes. So this is equal to 250 ohms. That is the load resistance. So what is IDC? IDC is equal to 2Im by pi, because it is a full wave rectifier. So 2Im divided by pi. So that is equal to 2 into, let us take the current is as 400 milliamperes, which is the maximum rated current. 400 divided by pi. Pi is 3.14. So this gives us the IDC as 280 milliamperes. Next, let us calculate the VDC. Voltage is nothing but the current multiplied with the resistance. So VDC is equal to IDC multiplied by RL. So IDC is equal to 280 milliamperes, and the load resistance we have already calculated, it is 250 ohms. So this is equal to roughly 70 volts. Next, let us calculate the DC load current. So IDC is equal to, we have already calculated, it is 280 milliamperes. Now let us calculate the peak inverse voltage. Peak inverse voltage is the maximum voltage which appears across the diode during operation. So when maximum voltage appears across the diode during operation, when the diode is in reverse bias. So PIV of full wave rectifier is given as 2 Vm. So that is equal to 2 into 100. So in this case it is 200 volts. It is 200 volts. Next, let us calculate the efficiency. The efficiency is given by the DC power delivered to the load divided by the AC power input. So the efficiency is equal to DC power delivered to the load PDC divided by PAC. So what is a PDC? IDC square multiplied by the load resistance. And what is the AC power? IRMS square multiplied by the load resistance. So this gives us the value of efficiency. So this is equal to, what is IDC for full wave rectifier? 2 Im by pi. And what is IRMS for full wave rectifier? Im by root 2. So into root 2 divided by Im. So this gives us the value as 8 by pi square. So this is equal to 80.99%. So this is the efficiency of this full wave rectifier. Now let us go to the sixth problem. The sixth problem pertains to the full wave rectifier. A 230 volt 60 Hz voltage is applied to the primary of the 5:1 step down center tap transformer for a full wave rectifier having a load of 900 ohms. If the diode resistance and the secondary coil resistance together has a value of 100 ohms, then you have to find out the DC voltage across the load, DC current flowing through the load, and DC power delivered to the load, and the rectification efficiency. So all these parameters have to be calculated in this problem. So the answer is the voltage across the two ends of the secondary is 530 by 230 by 5. So that is equal to 46 volts. So voltage from center tap to one end, it is 46 by 2. So it is 23 volts. Now DC voltage across the load VDC is equal to 2 Vm by pi. So 2 into 23 into root 2 divided by pi. So that gives us the value as 20.7 volts. So that is a DC voltage across the load. Next, DC current flowing through the load is given by IDC is equal to VDC by RS plus RF plus RL. So that is equal to 20.7 divided by 1000. So that is equal to 20.7 milliamperes. And DC power delivered to the load equal to IDC square into RL. So that is equal to 20.7 into 10 power minus the whole square into 900. So that is equal to 0.386 watts. So this is the solution for this problem. And the efficiency, which is nothing but the DC power delivered to the load divided by the AC power input, is given by VDC square by RL divided by VRMS square by RL. So that is equal to 20.7 whole square divided by 23 whole square. So that is equal to 0.81. So the efficiency is 80%. Next, let us come to the question number 7. This is the bridge wave rectifier which has a load resistance of 100 ohms and it is fed with 220 volts. And assuming the diodes to be ideal, we have to find out the DC output voltage, the rectifier efficiency, peak inverse voltage. So all these three parameters have to be calculated for this bridge amplifier. What is the circuit of bridge amplifier? This is a circuit for the bridge amplifier. It has 4 diodes. And the input is given across these 2 points, and load resistor is connected here. This is RL, and this is the transformer secondary winding which feeds the 4 diodes. Now in this problem, the primary voltage is 220 volts. Now let us assume that the transformer turns ratio is 10. Assume the transformer turns ratio is 10 is to 1. Now let us first calculate what is the RMS value. So VRMS is equal to Vm by root 2. So that is equal to Vm is equal to root 2 into Vrms. So what is the RMS value? It is given as root 2 into 22 volts, because we have assumed that it is a step down transformer with a turns ratio 10:1. So Vm is equal to 31.108 volts. Next, what is the value of VDC? Assuming that the diodes are ideal and assuming that the coil resistance is negligible, so we get VDC as VDC equal to 2 Vm by pi. So what is the value of 2 Vm? Vm already we have calculated. So Vm is equal to 31.108 volts divided by pi. Pi is 22 by 7. So we get VDC as roughly 19.796 volts. So that is a DC voltage. Now let us calculate the efficiency. Efficiency of bridge rectifier is same as the efficiency of low rectifier, which is roughly 81.2%. So this is equal to 81.2%. And PIV of the bridge rectifier, it is Vm. Whereas for a full wave rectifier it is 2 Vm. For a bridge rectifier, the same voltage 2 Vm is shared by 2 diodes. So we get the PIV value as Vm. PIV equal to peak inverse voltage so that is equal to Vm. So Vm is nothing but 31.108 volts. Next, question number 8. Show a diode clipping circuit to convert 1 kHz sine wave of 20 volts peak to peak to a symmetric square wave of 4 volts peak to peak amplitude. So this is the problem. So here we don't get a perfect square wave using a diode clipping circuit, but we get near to a square wave. So let us find out what is the clipping circuit, which converts 1 kHz sine wave of 20 volts peak to peak to a symmetric square wave of 4 volts peak to peak. So this is a positive clipper circuit using a diode. So in this case, we give a voltage of 4 volts here, and let this we call this resistance as R1 and this resistance as RL, and this is the input Vi. So this is the positive clipping circuit. Because we have provided a 4 volts here, this gives the output like this. Now let us say the input is like this with a peak value of 20 volts. So this is plus 20 and this is minus 20. So this circuit will give us this waveform. So it is clipped at plus 4 volts. Why? Because initially when the voltage is less than 4 volts, then this diode is reverse biased, and whatever voltage you give at the input, it appears across the output. And when the voltage is more than 4 volts, then this diode is forward biased and the voltage is clipped to 4 volts. So we get output like this. Next, when you use a circuit like this, this is a negative clipper circuit, and this negative clipper circuit will clip the negative portion of the waveform, which is more than minus 4 volts. So this gives the output voltage like this. So this is minus 4 and this is plus 20. So this is a negative clipper circuit. And this is positive clipper circuit. So when you combine these two, then you get clipping at plus 4 volts as well as at minus 4 volts, and nearly we get a square wave. So combining these two, we get combining the above two circuits, we get so this is a positive clipping circuit, what we have done in the beginning, and this is the negative clipping circuit with minus 4 volts, and this is the load resistance RL. So this circuit, it takes this input with 20 volts peak to peak and it gives the output like this. So it produces a square wave, not a perfect square wave, but nearly a square wave it produces. Now let us go to the ninth problem. The ninth problem, a 230 volts 50 Hz voltage is applied to the primary of a 4:1 step-down transformer in a bridge rectifier configuration having a load resistance of 600 ohms. Assuming the diodes to be ideal, so compute the DC output voltage, DC power delivered to the load, PIV, and the output frequency. So all these parameters have to be calculated. We have already done bridge rectifier problem. So on the similar lines, let us solve this problem also. So Vrms is equal to Vm by root 2 and Vm is equal to root 2 into Vrms. So this is equal to root 2. Vrms is 230 volts. But it is a step-down transformer, so let's take this as 230 by 4. So this is equal to roughly 81.3 volts. Next, let us calculate what is the VDC. VDC is equal to 2 Vm by pi. It is the same value as the full wave rectifier. VDC is equal to 2 Vm by pi, and that is equal to Vm already we have calculated, and that is 51 point. It is already 81.3 volts. So VDC is equal to 2 by pi into 81.3. So that is equal to 51.78 volts. So that is the average DC voltage. Next we have to calculate what is the DC power delivered to the load. So that is equal to IDC square multiplied by RL. So PDC is equal to IDC square multiplied by RL. So that is equal to, we can also write as VDC square divided by RL. VDC we have calculated, it is 51.78 volts. And the load resistance is 600 ohms. So divided by 600. So this is equal to 4.46 watts. So that is the DC power delivered to the load. And what is the peak inverse voltage? PIV equal to Vm, and that is equal to 81.3 volts. And output frequency, the input is 50 Hz and output is twice the input frequency. So output frequency equal to 2 into 50 Hz. So that is equal to 100 Hz. Now let us go to the last problem. The last problem is a half-wave rectifier having a resistive load of 1000 ohms rectifies an alternating voltage of 325 volts peak value, and the diode has a forward resistance of 100 ohms. Calculate peak, average and RMS values of current, DC power output, the AC input power and the efficiency of the rectifier. So what is the peak value of current? Im equal to Vm by Rf plus RL. Rf is the diode forward resistance and RL is the load resistance. So here that is equal to 325 divided by 100 plus 1000. So that is equal to 295.45 milliamperes. The average current is equal to Im by pi because it is half-wave rectifier. If it is full-wave rectifier, it is 2Im by pi, twice the value of half-wave rectifier. But here, because it is a half-wave rectifier, IDC is equal to Im by pi. So that is equal to 295.45 divided by pi. So that is equal to 94.046 milliamperes. The RMS value of current, IRMS equal to Im by root 2. Sorry, Im by 2 because it is half-wave rectifier. So that is equal to 295.45 divided by 2. So that is equal to 147.725 milliamperes. What is the DC power output? IDC square multiplied by RL. So that is equal to 94.046 into 10 power minus 3 whole square into 1000. So that is equal to 8.845 watts. And the AC input power PDAC is equal to IRMS square into RF plus RL. So that is equal to 24 watts. And what is the efficiency? PDC by PAC. So 8.845 divided by 24, 36.85. So the efficiency of half-wave rectifier is poor. We have already calculated the efficiency of full-wave rectifier and the bridge rectifier. We got the values as 81.4. But here for half-wave rectifier, the efficiency of rectification is almost half of full-wave rectifier. In this case, it is 36.85%. So these are all the problems from the part A of question bank of unit 1, that is the diode applications. So with this I conclude today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.